نحن في سكيلز بيت الخبرة ملتزمون بالجيمات الثلاث: جديد، جيد، جدوى.
Here are the two equations. Are derived simultaneously. And the result here will have a state vector. It has the mechanical displacements as well as electric displacements. In the first method, here the state vector has only the mechanical displacement. And we said that this vector is equal to U and D. Here is the rod and divided into elements. This has node I, node J, the piezoelectric material. This is the rod, and then each node has mechanical degrees of freedom associated with it and electric degrees of freedom. Mechanical degrees of freedom and electric degrees of freedom. And maybe when you look at this type of formulation, you could see why this D was named electric displacement. Because you could see that we write the state vector as a mechanical displacement of the nodes as well as the electric displacements of the nodes. And then for this element, we said that this is as dimension length L of the element. Then we can write down the energy equation for the composite assembly. And we write down the kinetic energy. And we have combination of the piezo and the rod. So this would be A rod, density rod, A piezo, density piezo, and then integral of U dot square and dx. And then we write down the potential energy. And this is equal to 1/2 the integral from 0 to L of the strain times the stress in the rod, the stress in the piezo, dV, which is the volume of the element, plus the integral from 0 to L of d, e, and dx. I'm sorry, dv. And last lecture we said the first part is the mechanical energy. The last part is the electric energy. And the S is the strain. Capital T is the stress. And then dV is the volume. Okay. And now the last part that we need is the work done. That is interchange between the shunted network and the rod. And we said this is equal to the voltage times the del charge. The voltage that we send it to the network, for example, if we take this, and put a network of resistance and inductance, inductance, I'm going to call it L sub I. Then we can write this as energy that goes into the resistance and goes into the inductance. And I can rewrite it as, and this I is the current that flows into this shunted network. And I can rewrite this as minus Li, and then I replace each current by the derivative of the charge. So this will be L Q dot, so it will be Q double dot, and then R Q dot del Q. So if I'm going to write this in the coordinate of the charge, this would be my non-conservative voltage. Or non-conservative force, if I write this as force del X. And then del Q. Okay. But I'm going to write everything in terms of the electric displacement instead of the charge. And before we do this, we have all the components that we need: the energy, kinetic and potential, the work done by the external circuit on my structure. So now we can write it either in Hamilton principle or we can write it in Lagrange dynamic form. Okay, so for example, here to do either one of them, we have to say now, assume the following shape functions. So we assumed here that u is equal to a1 plus a2x. And from here we extracted u in terms of ui and uj. And we wrote this, ui and uj. And this will be 1 minus x over L, x over small l. So when x is equal to 0, then this will be 1 and this will be 0, and u will equal to ui. And when x is equal to L, this term will disappear, this will be 1 and u will equal to uj. And similarly, I'm going to assume that the electric displacement D is equal to same form. For example, B1, B2x, and then we do exactly what we've done. So we can rewrite this in terms of the displacements di and dej at the two nodes, I and j, 1 minus x over L, x over L. And then now we have complete description of these vectors in terms of the corresponding nodal parameters. And I said I'm going to combine them in one vector now. And this will be like this, ui, di, uj, dj. That's if you want to do it like this, and if you want to separate the mechanical displacement alone and the electric displacement alone is fine. Okay, so now this will be 1 minus x over L, 0, x over L, 0, 0, 1 minus x over L, 0, x over L. And then now I'm going to call what we have now N1 and N2. And then this vector is the deflection vector delta. So this is all delta. This first vector is my N1. The second vector is my N2. So now I can say now, then in general, whenever I have u, I can replace u by N1 and delta. This vector is 1 by 4. This delta vector is 4 by 1. So we have a scalar representation of u. And the N1 is function of x. Wherever we are interested to determine the displacement, we just plug in the proper x in the local coordinate system inside the element. So this is my local coordinate system. X, this node, x is equal to 0. This node is x equal to small l. And then similarly, I can write down the electric displacement as N2 and delta. Of course, from here, then the strain partial u by partial x will equal to partial N1 by partial x and delta. N1 is a function of x, and N2 also is a function of x. Now the kinetic energy is very simple and straightforward. So I'm going to replace each u dot by N1 delta dot. N1 delta dot. The N1 has 0 and 0. So it has only the contributions of u and u. So that's why this u is only the mechanical displacement of the structure. And as we get at the end, you will see this term is capacitive element, the capacitance. So the capacitance acts in mechanical system as a spring. So this is valid in the potential energy. Here, the external non-dissipative or non-conservative loads, I can only put the resistance because this is actually what dissipates energy. And I don't need to put the inductance because the inductance acts as a mass. And this mass I could have put it here because it will have contribution in kinetic energy. And that's what you will see at the end. That's what will happen to it. But intuitively, we as mechanical engineers, we don't know where to put this directly. So I'm putting it as a non-conservative external loads. Its contribution will appear as an inertia term. So now we look at the kinetic energy. So I can write down T kinetic energy is equal to 1/2. And then we have these terms, A rod, rho rod, A piezo, rho piezo, and then the integral from 0 to L now. We have dx, and I'm going to take each u and replace it by n1 delta. So this would be n1, and then the delta, I'll bring it here, dot, and then I replace the second u dot by delta dot transpose and n1 transpose. Of course, these two matrices, this is 1/4, the transpose is 4/1, so the result is 4/4. And I can combine all these in one matrix, and this would be our mass matrix. Now for the potential energy, we need to remember for the piezo, we wrote down the equations of the constitutive equation of the piezo. I wrote them down in terms of the strain and the electric voltage. And these were given as a function of the stress and the electric displacement. And here we have H and minus H. And then here we had 1 over epsilon S. And the denominator here had 1 over SD. Forgot. So this would be 1 over CD, or 1 over SE, which is, this is Young's modulus of the material. So this CD is 1 over SE, 1 minus K squared, the electromechanical coupling factor. And H was D over SD epsilon LT. Okay, we don't need all this. Here we'll just write down that U is equal to N1 delta, and electric displacement is N2 and delta. And the N1 and N2 are functions of X. Okay, so now we'll go into the second equation. I'll replace the stress and the piezo and the rod by their corresponding equations, and here replace the electric voltage by its corresponding equation. The way this here T and S. So now here we'll use the constitutive equation. To rewrite the potential energy as follows. The potential energy now will equal to 1/2 integral the strain is U of X, partial U by partial X. Now I'm going to break down this to two pieces. The stress on the rod, and then dV, and then the strain times the stress of the piezo dV. So the stress on the rod is equal to E rod U of X. This would be my T rod. And then the dV at any x, I'll take a small element, dx, and the dV will equal to this dx times the thickness of the rod times the width of the rod. So we'll say that this is thickness of the rod. So I can replace this dV by dx times the thickness of the rod times the width of the rod. Okay, And these two combined are the area of the rod, cross-section area of the rod. Okay, and then here plus 1/2 integral S again, and then T piezo, I'll replace it from here. So T piezo will equal to C D and S minus H and D. And then dV. Now for the piezo, this would be dx, and then I'll have the thickness of the piezo times the width of the piezo. T piezo and B, and this would be the area of the piezo, cross section, AP, and the integral from 0 to L. And then the last term, one-half integral from 0 to L, and then, sorry, let's leave this for a minute. The displacement D times the voltage, and this occurs only in the piezo, so I have to take the value of it from here. So this would be minus H and S plus 1 over and D. And then the D volume, again, dx, and then T piezo, and then B from 0 to L, so this would be A piezo. Now, we have everything now written in terms of two parameters. Well, not exactly. We want to obtain one more thing. Then now, U potential energy. From here, I'll replace U of X from here in terms of N and delta. This will be 1/2 A rod, and then E rod, I'll bring it outside, so this will be E rod, and then the integral, we'll leave this for a minute, ux squared dx, and then here this will have two terms. The first term is 1/2 A piezo, and then this C piezo, I'll bring it out, so this will be C piezo, and then integral from 0 to L of Ux and S dx. S is the strain, so I can replace the strain by U of X. And then I have minus 1/2 A piezo times H integral from 0 to L of Ux and D and dx. And then I have another half AP times H, I'll take this H out, integral from 0 to L of D U of X dx. Okay, so we finished this term completely. This and this. So we have, and then the only term left now is the last term here. then plus 1/2 AP, and then 1/epsilon S, and then the integral from 0 to L of d and x. So if you look at what we have three distinct groups. One group depends only on mechanical displacements. One group only depends on electric displacements. And then this middle group has both of them, mechanical and electric, mechanical and electric. So this is coupling terms between mechanical and electric. Okay, we don't need all this now. And if you look again to these three groups, you will see I have everything written in terms of two parameters, the U and the D. The U and the D are again the main components of the state vector that we are working with, mechanical and electric displacements. So I'm going to replace them in terms of N1 and N2. So now here, this will give me all the mechanical stiffness. This will give me all the electric stiffness, and this will give me the electromechanical coupling stiffness between these two terms. Okay, so now the first term, if you look, the integrals are exactly the same, U squared and U squared. And these two terms are combined. So this is the area of the rod, Young's modulus of the rod, area of the piezo, Young's modulus of the piezo. This is the reciprocal of the compliance. So now we combine these two, and this will be U potential energy will equal to 1/2, and then here will be A rod, E rod, plus A piezo, C piezo at open circuit. Okay? And then now the integral of the U squared, I can do it like this. Integral from 0 to L of N1 partial derivative with respect to X transpose, N1 partial derivative of X, everything in dx, and then I'll factor out here the delta, and then here the delta transpose. So now we finish these two terms. I'll do the last term. This will be 1/2 A piezo epsilon S, and then now 0 to L. Each one of these D's, I'll replace it from here by N2 delta. So this will be N2 transpose N2 dx, the delta, and the delta, oops, transpose. The last term, all of them are given by the negative term. So I have here minus 1/2 A D and H now if we replace this from here, so this will be N1 X transpose, and then N 2 dx, and then here the delta. These two matrices are different. N1 and N2 are different. So N1x transpose N2 is not the same as N2x transpose N1. They are different. So I have to do this alone and then add to it this term alone. So this will be here. Here I'm beginning with N2 and then N1 X transpose. Then now we're done. We can, we're done from this part.
N2 transpose N1x.
Pardon? N2, I'm sorry. Okay, so now if we look at what we have, this matrix our mechanical stiffness matrix, and I'll call it K S. This is mechanical stiffness. The second equation this will give us the K electric or the electric stiffness. The last term is the coupling matrix. Oops, we have here, we should have here delta transpose. K coupling, and this is the coupling stiffness. Now each one of these is function of N1 and N2. We put these numbers in Mathematica, we extract each one of these matrices. The last matrix that I want to calculate is this component. And we'll see here as del W is equal to minus L Q double dot plus R Q dot del Q. My independent variables that I'm using is the electric displacement D. So I have to replace each Q by terms of the electric displacement. Electric displacement is Q per unit area. Q per unit area. So now I can replace each Q by the integral of Q dA. Okay? And of course, Q dot will be the integral of D dot, dA, and so on. And del Q will equal to del D dA. Okay? The A that we have here is this A. Is the surface area of the piezo. The charge that we have per unit area of the piezo surface, not the cross-section area. Okay? So the area of the piezo will be L And yeah, sorry, the dA, we have to do it like this. This is dx, and this is b. So I'm going to take the a and replace it by b dx. Okay, now I'll take these and plug them in del W. So this will equal to minus L. Q double dot will equal to the integral from 0 to L of d double dot b dx. Oops. This L, as we said, this is the inductance, so we'll just give it L sub I. So we don't mix it up with the length, small l, okay? So we'll give this small l. And then here plus b r integral. Instead of q dot, I'll write it as d dot dx. And then the last term, del q, I'll write it like this. B integral del d and dx. Now we go back again to here. Replace each d by n2 delta. So now we have b squared out. And then we have li integral. Okay. Now d double dot, I can replace it by for example n2 transpose. Oops. Okay, and then we have delta double dot transpose dx. And then this, I have r, and I replace the delta dot by delta dot transpose integral, and then n2 transpose dx. And then now what is left, I took this b here, so I have b squared. So I still have this integral. This integral, I'm going to replace it like this. It will be integral from 0 to L of n2 dx. And then I have here, I'm going to make this del. So this will be del. So this will be here. Times del of del. I'm going to take all this . This, and then we can write them down here. All the term inside this red bracket is multiplied times del of delta. My deflection is delta. So this is very similar to, I can write this as force del x. So all the term inside this red bracket, this box, is my non-conservative force acting on the system. And this is my virtual displacement vector. Okay. Now we're done. We have the mass matrix. We have all the stiffness matrices. We have the force vector. We just put Lagrange equation, combine all of them in one term. And this now gives us I have M delta double dot plus K S K electric minus K coupling times delta, and this will equal to delta double dot minus this matrix. This matrix, I'm going to call it M electric because it multiplies delta double dot. This matrix, oops, I'm sorry. Okay, so this whole thing is the mass electric component. So this is minus here. So this is Li integral N2 transpose dx b squared, and then times 0 to L N2 dx. And then minus the second component, and I'm going to call it C electric because it's multiplied by delta dot, and this C is B squared R integral from 0 to L N2 transpose, same matrix, dx, 0 to L, N2 dx. So this would be the electric inertia. This would be the electric damping that comes from the shunted network. So this is the electric inertia matrix, or electric mass matrix. And then this is the electric damping matrix. Now, if you look at the final result, what the piezo shunted network did, you will see that this term, we have negative here, but when you do the multiplications of the matrices, you will see this negative becomes positive. So what the piezoelectric material did, added stiffness, added inertia because this is negative term, added damping because this is negative term. Everything will come to the right-hand side, will increase the inertia, increase the stiffness, and increase the damping. Now, all these matrices, please distribute, Mario. Just write down this M here, plus M electric, delta dot, plus C electric, delta dot, AS A electric, equal to 0 or equal to any external force vector. In the handout that you have, I give this the symbol VL, and I give this the symbol V sub R. This is the mathematical program. I put the N1 and N2 from here, and then I get their derivatives. ND1 and ND2 are the derivative of N1 with respect to X, and the derivative of N2 with respect to X. So we have these two. Now I want to get the mass matrix. So it is N1 times N1. N1 transpose times N1. So now N1 times N1, and I'm using the outer product, so I'm getting the N transpose. So now once I have this matrix, integrate this matrix, which is the inside N1 transpose N, integrated from 0 to L with respect to X. So now we get the mass matrix. And then now we go into the three other matrices. I can calculate the structure matrix. A total, E total, which is the first term. The total area times Young's modulus for the rod and the piezo. And then I need to integrate the derivative of N1 times N1 derivative. So now I make the outer product ND1 derivative 1, ND1, get the product, integrate it, multiply it times the area, and so on. The final result is all these 6 matrices that we have, and each one of them in terms of all the properties of the rod as well as the piezoelectric material. And the last 2 matrices, you can factor out this term. 1/4 B squared, L squared, Li is my inductance. You can factor this out. The result will be like this. Both of these matrices will look like this. 0, 0, 0, 0, 0, 0, 0, 0, and then so these two matrices are symmetric. All the matrices that you will get are symmetric. So this is symmetric mass matrix, symmetric stiffness matrix, and so on. Now if you look at this, and here I could commute these two. I could make this N2 first and then N2 transpose. So it doesn't matter where you put the transpose in this because it's the same matrix. The N1 and N2, you cannot commute. So you have to make the first one plus the second one. First one plus the second one. Okay? Now we have this. Then you look at last lecture, I give you the handout for the time domain model. The most important thing is the parameters, which we erased. Okay? The most important thing is, for example, here, Young's modulus of the material. Young's modulus of the material. Young's modulus of the piezoelectric material is here when it is open circuit. When it is open circuit. Young's modulus that we get for the regular material, C, E, when it is short circuit, are completely different. The factor that combines them is the electromechanical coupling factor. So we have SE, 1 minus K squared, is equal to SD. If I take the reciprocal of this, then I have the Young's modulus at shunted circuit, Young's modulus at open circuit, 1 minus K squared. So you put the properties from the beginning. This is not the regular Young's modulus, this is the Young's modulus at open circuit. And then now, the epsilon. The epsilon that we have is epsilon to the power S, or superscript S, which is at constant strain. I have epsilon at constant stress, and then I have to modify it by the electromechanical coupling factor. So you have to convert the constitutive equation correctly according to the formula that we have. And then now, I used exactly the same tuning parameters as the previous circuit. The same inductance and the same resistance. And then now here, I initialize all the matrices as zeros. The stiffness overall, the mass overall, the damping overall as zeros. And then now I say, this program you can modify very easily if you have any number of elements. And some elements will be plain rod, some elements can be rod with piezoelectric on it. So now here, the multiplier for the mass matrix has all the parameters, the A rod, rho rod, A piezo, and rho piezo, and so on, as we described last time. And then now here the last term is the term that we get from mathematical equations. The quarter, B squared, L squared, and R. So BL squared times R, BL squared times Li, and so on. So now we have all the matrices. You see here, I calculate the coupling, and then I add to it coupling transpose. This and its transpose. then we have all these. Then now I get the total mass matrix, which is the combination of the mechanical and electric, the total stiffness matrix, and then the damping matrix. Then now we go into this part, is to assemble the matrices for different elements. And then the last part, here, I assemble all of them, and then now put the boundary condition for a fixed rod. So now I reduce the stiffness matrices and mass matrices for a plain rod now to a rod with fixed end. And then we go into writing down the system in state space representation, get the inverse of the mass. So this will be 0, identity, minus M stiffness, minus M inverse, C matrix. This is state space representation. I'll write it in a minute. And then the last, once we have the A matrix, we can calculate the damping of the system. And then this part is to calculate the frequency response of the system. Okay? This will be very clear when we do the homework. So once you do the homework, this will be super clear. And then the last part that we described at the end of last lecture. When we do the frequency domain finite element, that's the result. When we do the time domain element, we are again approximating the displacement and the charge by linear functions. So the results don't compare exactly to this unless we increase the number of elements. So for a single element, that's what we have. The frequency is shifted from the main frequency that we calculate with a frequency domain model. And then as you increase the number of elements, they line up, and then you increase more. Then you start homing on this peak that will have leveled plateau. And again, each one of these cases is very similar to the GHM model. 1 oscillator, 2 oscillator, and 3 oscillators, and so on. I described piezoelectricity, I think, is more than enough. And what remains is this homework that's coming on Tuesday. You will use, which I did not describe, the impedance matching to compare it with these results. Okay, and then we'll try a couple things with a different number of elements. So you can see how this all fits in one package. Okay? It's fine. Still have 6 minutes. We'll just begin the what we're going to describe in next lecture. This equation that we did was when these two elements were in series. Okay, if these two elements are in parallel, this needs a lot of tricks. Okay? Because if these two elements are in parallel, then this is not going to be a straight equation like this. And to accommodate this, we have to use an internal variable very similar to GHM. So you can make everything nice and linear. Because if it is not, then this is the reciprocals. So you have to make some internal variable modification. That's all what I'm going to say, and we will not do it in the homework, so you just keep it in your head. Yes, the section that will begin is the constraint layer, damping, and the name applies that implies that we have. For example, I'll begin first by looking at rods. In spite of their simplicity, they show very important characteristics. And for example, if I take a rod like this and then put viscoelastic material on it, and then stretch this rod, then the viscoelastic material will move along with the rod. If the rod becomes like this, the viscoelastic will follow it. And this is viscoelastic material, and here is rod. And the motion of the viscoelastic will follow the rod, and this arrangement is called unconstrained viscoelastic material. And the mechanism of stretching and compressing the viscoelastic material as the rod undergoes vibration, the mechanism here is elastic or longitudinal damping. Now, we'll see why this is not very good, and we have another mechanism where the viscoelastic material now, instead of free layer, we come here and put a constraining layer, piece of metal. This metal can be as thin as an aluminum foil. You can buy these materials, 10,000ths of an inch rubber material, and coat it from the outside by 10,000ths of an inch aluminum foil. Okay? So this constraining layer does not have to be a very massive piece of steel, unless your structure is massive. So we will see the tuning of these things together. But many manufacturers give you a roll that has tape that you peel out from one side, and on the outside it has this aluminum foil sheet, and you can lay it down on any vibrating surface. The way we lay it down, we don't have to use many square meters of this material. We will see when we analyze the rod dynamics, we'll see the optimum length of this material. So we have here, this is a constraining layer. And then this is my viscoelastic material. And this is, for example, can be my rod or beam or plate and so on. So now, if now the rod expands during the vibration and it takes this position, the outside constraining layer is constraining the motion of the layers of the viscoelastic layer attached to it. So they will not move as much. But because the plate or the rod is expanding, these have to follow. But they will maybe go this much only. And now the final form of the viscoelastic material will look like this. So now the viscoelastic material has shear. And this mechanism is more effective than the longitudinal stretching and compressing of the damping material. So this is called the constrained viscoelastic material. And the mechanism of damping here is shear. And this is very effective in damping structural vibration. And this goes back to, we'll say, in 1958. And the people that develop it are people from BBN, Bolt, Brannick, and Newman in Cambridge, Massachusetts. So they developed this idea, and this idea has been around for these 40 years. Everyone in the vibration area should try this first. This is number one. If it doesn't work, then you try something more sophisticated. But in most cases, this might be good enough for many applications. So you always try damping material. If you want to try the piezoelectric material, has a lot of potential as passive damping. Along goes this. Along goes this. We can also come make this viscoelastic, and on top of it we put the piezoelectric material. So you can use the piezoelectric material and dual function for constraining and also for adding additional damping. So you can take a bare material, bond the piezoelectric material to it so it can add additional passive damping. If everything here doesn't work, then you go to active control. But you always have to have a backup as a passive damping treatment. Good evening, I will see you on next Tuesday. Constraint layer. Today we'll start by looking at energy, dissipation, in constraint layer. The constraint layer is used with rods to dampen the longitudinal vibration. Constraint layer damping of longitudinal . The main purpose of this is to find the optimum length of the constrained layer damping. Here we'll use the very important reference by Plunkett and Lee. And this is called length optimization. Constraint, visco, elastic, layer damping. And this paper is in Journal of the Acoustic Society of America. Is in volume 48, number 1, pages 150 to 161, and 1970. This paper talks about this case, and I will show you at the end that we can also use it if we have bending or transverse vibration acting on beams. And this paper is, in spite of the fact that it is 30 years old, it's the only reference now that you can use to design constrained layer damping. And the numbers that you get from here are guidelines for anyone that design constrained layer damping. And the power of it is the numbers that we get are universal. So you have a single number to design constrained layer damping. So it's very powerful method. And I'll begin with this, and then we'll look at the second part. We'll look at transverse vibration. And then instead of just pure damping, we'll make it active damping. So we will go through these steps: longitudinal vibration, transverse vibration, and then active damping. So the steps now that we will do: number 1, passive, constrain the layer. Damping. And this is called, the abbreviation is PCLD. And longitudinal vibration. Number B and transverse vibration. And then the second item is we'll repeat all this for the active case. Active, constraint, layer damping, and the name will begin with A, so it will be AC LED. We'll look on a constraining layer, viscoelastic layer, and a structure. This is our viscoelastic material, and then we have here a constraining layer. This is layer 1, this is layer 2, and this is thickness H1, thickness H2. And this will have x-axis, and the origin I put it in the middle of the constraining layer, so this distance is L over 2, this distance is L over 2, or minus L over 2. Okay. Then now I'll take this and make a free body diagram of it. Layer 2 and layer 1. Here we have stress, sigma 2, and then in the positive axis we'll have sigma 2, partial sigma 2, partial x, dx. So we have stress increasing in the positive x direction, and we'll have accordingly resistance from the viscoelastic material, which is the shear stress. That counterbalance this normal stress. And then we have the counter balancing shear stress on the viscoelastic layer, equal and opposite. And then we have come and look now at the performance when I come and excite the lower structure by epsilon 0. So epsilon 0 is constant, longitudinal, strain of the base structure. And okay, so now this moves some epsilon 0, and this will move a distance u 0. This would move a distance u. The u is the same mu as the structure. And then the difference between these two is the shear angle gamma. But I'm going to make it like this, so it will be positive gamma. And this is my shear angle. Well, let's just say here that this is B white. Okay, so now we'll do equilibrium. And I'm going to do this for quasi-static equilibrium. So now, for example, on the top layer, the constraining layer, we have the excess normal stress, partial sigma 2 by partial x dx. This is stress multiplied by the area on which the stress acts. So this is equal to the thickness, which is h2, and then it's acting perpendicular to the board, distance b. So this is in equilibrium with the shear stress times the area the shear stress is acting on it. And I'll take this distance is the dx. So the shear stress is acting on, so we'll say here where sigma is the normal stress and tau is the shear stress. So now from here we'll drop the B and the B, the dx and the dx. And I'm going to make also, but the shear, the normal stress is equal to Young's modulus times the strain, which is partial u by partial x. So this is Young's modulus of the top constraining layer. And this is the strain of the top layer. So now this, if I take this and differentiate it partially with respect to x, then this will equal to E2, and then second derivative of the displacement, longitudinal displacement u, so this will be ux and x. Okay, going back again on all this, in view of this, what we will try to do is find U. Find the deflection of the constraining layer for a given deflection for the base structure. So if we know this as an input, we get this as an output. The result between these two will give us the shear angle of the viscoelastic material, because the shear angle, I can get it from this triangle. From this triangle, this distance is the difference between U and U0. And this distance is the thickness of the viscoelastic material. And now I can calculate the shear angle will equal to U minus U0 divided by H1. Okay? So now for a given input, I'll determine how the constraining layer will respond. And from this, we determine the shear angle. You will see very important characteristic. When I am here, there will be no shear angle. When I am here, I have the maximum shear angle. When I am here, I have the minimum shear angle. Anywhere in between will be somewhere in between. So now, if I want to get the maximum energy dissipation, I have to stay here and here. Okay? Because the middle is not very good. So now if I want to get the energy dissipation per unit volume, I want to make this as small as possible, but I want to dissipate the maximum by staying here. So this will give us a balance between how much I want to dissipate here per unit volume. And the result will be this, the optimum length. So now, to summarize all this, for this analysis, the purpose of the analysis number one, find U for a given epsilon 0. Okay. Number two, find gamma, which is the shear deformation. Number three, find the energy dissipation. And I know that this is the integral of the shear stress and gamma dV, which is very similar to half the stress times the strain. Okay? And I can rewrite this in terms of the loss factor integral over the volume, and replace the shear stress by the loss, by the loss modulus, how much I dissipate, times the angle. So this would be angle and another angle, so this would be angle squared d volume. So now you see, if the angle is big, the energy dissipation is very, very big, because I'm squaring this term. I'm squaring this term. Now, so for a given this, I'm going to determine this, and I'm going to determine the energy dissipation. And then the last step here, find the length of the constraining layer to maximize this energy dissipation. Okay. If the length is very big, I have only the edges are active by their motion, the rest is not. And so I'll have some energy dissipation. If this is too short, I don't have enough to dissipate energy because the volume is very small. So there must be somewhere in between. The bottom line of all this, if I have a structure and I want to put damping material on it, I don't put damping material all over the structure. Because if I do, it will not be optimal. So we come and do something like this. This is viscoelastic, and then I put the optimum length on it. And then I leave a space and put viscoelastic. And put treatment on it, and so on. And this configuration, this is the optimum length. And so on. And this is called segmented constrained layer damping. Okay, so this is the L optimum that we like to determine. Okay, so now we have the first equation for the constraining layer, and then now I'll take this and then plug it here. So we have E2 times H2 partial sigma 2 by partial x is U of x and x, and then this is equal to shear stress. Now we go here into the viscoelastic material. This is number double I. I have the shear stress is counterbalanced by the shear deformation and the shear modulus. And I'm going to write the shear modulus like this, because it's a complex number. Okay, so this is the shear modulus. So this is like the constitutive equation of the viscoelastic material. This is the shear deformation. And now this will be G asterisk, and the gamma, we write it down in terms of the U and U0 and H1, the thickness of the viscoelastic material. So now from here, then I have H2, E2, Ux and X is equal to, I'll replace the shear stress by what we have here from the constitutive equation. So this is G U minus U0 over H1. And I'm going to clean this equation. So I'll have H1, H2, E2 divided by G asterisk, U, X, and X. And I'll bring the U here, and I'll leave this U0 here. And I'm going to call all this number B asterisk squared Ux and X minus U and here where the B asterisk is equal to the square root H1, H2, B2, G asterisk. The thing that I wrote here for quasi-static equilibrium, because I looked at the stress and we counterbalance it by the shear of the viscoelastic material. We did not put the inertia of the viscoelastic material, of the constraining layer. If this material is relatively thin, the inertia will be negligible number. Okay? So that's the approximation that we have. We put in equilibrium static forces, whatever stretch we put in the constraining layer, we counterbalance it by the resistance of the viscoelastic material. So the equation now that we have and U0, I can calculate it from the strain. The strain is constant, so if I integrate the strain over the length, I can get a deflection here. So this would be epsilon 0 and x. Again, we have partial u by partial x is equal to the strain. Then from here, I can say that u is equal to integration of the strain with respect to x. So if this, I want to get the deflection of the bottom structure. So this would be u0, epsilon 0, u0, epsilon 0, and if I integrate this from 0 to any position x, so this will equal to epsilon 0 and x. Now this is second order differential equation. It has a homogeneous term. It has a particular integral. I can combine these two and get the general solution. So the general solution is equal to u, and it has two components, u complementary function, u particular integral, the particular integral is very easy. We can get it from here directly. Will be epsilon 0 and x. The complementary function is the solution of the homogeneous equation. And the homogeneous equation is b squared uxx minus u is equal to 0. This has a characteristic equation b lambda squared minus 1 and u is equal to 0. And this gives us the lambda is equal to plus or minus 1 over beta s. Okay, or u complementary function will equal to some constant a1 e to the minus b asterisk x plus another constant a2 e to the plus x over b asterisk. Now I have two constants, the integration constants. I can determine them from the boundary condition. In here, the top constraining layer will deflect, will move. But I don't have any normal forces acting on it. So the normal force at the edges is equal to 0. Or we can say that partial u by partial x is equal to 0 at x is equal to plus or minus L over 2. This should be ideally E2 times the area of the constraining layer perpendicular to the board times the strain is equal to 0. I don't have any loads generated at the ends. So at these 2 points, L plus 1, L over 2 and minus L over 2, the strain is equal to 0. So now I have two conditions, two coefficients, I can determine the solution. Just take all this out. I'll just put this here. Then now u will equal to a1 e to the minus x over a2 e to the plus x over, and then we have plus epsilon 0 and x. And then now compose partial u by partial x is equal to 0 at x is equal to plus or minus L. Then we'll find a1 and a2. two are the negative of each other. And this will equal to minus epsilon 0 B shine L over 2 B asterisk, and then shine L over B asterisk. And from here we have a U. We'll find it to be equal to epsilon 0 x minus B asterisk shine x over B over to shine L over So from this equation, when you look at this equation, when x is equal to 0, u will equal to 0. So the constraining layer at this location does not move. It moves here and here. This is the maximum and maximum deflection. In between, there's nothing. So this is very small deflection. This is very large deflection. If we approximate the shine by a linear function x, so this would be straight line, moving from 0 to the maximum at these two ends. Okay. Now we want to go and calculate the, from here of course we can calculate, let's say as gamma is equal to u minus u 0 over h1. Then now from here the first term is epsilon 0 and x. This will be u0. So this would be u minus u0 will be on the left hand side, and the right hand side is equal to minus epsilon 0 and shine, and then the denominator is shine. Oh, sorry. And then we divide all this by h1. Gamma. Again, the same story. At x is equal to 0, the shine is equal to 0. I don't have any shear strain in the middle. When this is maximum, I have maximum at the edge. So now this is the middle of the viscoelastic material is ineffective in energy dissipation. The middle zone. Okay, now we'll the energy dissipation. we'll get the energy dissipation. Per unit length per unit width per cycle of vibration. And I'm going to call this D, energy dissipation. And this will equal to G double prime. The loss modulus times gamma squared, okay, and then times pi, and then per unit length and per unit width, so B and L, so this would be times H 1. Let me just go so you can see where this came from, so it will not make any confusion, you know. So this, what we're trying to do is like this: integral from 0 to 1 cycle, period of 1 cycle. And then here we have the shear stress times gamma d gamma and then so this would be the energy dissipation per unit volume, and then I'm going to multiply this by H1. So this is the energy dissipation per unit length per unit width. Okay? So this is stress times the strain, force times dx. But this is stress and strain, so this would be the energy dissipation per unit volume. I'm going to multiply it by the thickness, so I have the energy dissipation per unit length and per unit width. Now, how this comes in the picture, I'm going to make this divide by dt and multiply times dt. And then I want the average per unit cycle, so I'm going to divide by 1 over t. Now I'm going to replace G the shear stress by the shear modulus and the strain. This would be 1 over T, write down T is the period. And then now I'll replace this by G double prime, and then integrate gamma dot, and dt from 0 to t. And we've done this in the vibration class. If I have stress, if I have viscous damping, and I have displacement, this is sine and cosine, multiply them, integrate, divide by this, so it will become this term. So the final result of all this is this side. Now, I want to calculate the total energy now if I have certain lengths of the damping treatment. Then now here, del W will equal to the integral of what we have here. And the integration will be from minus L over 2, L over 2. Now I have gamma here as function of x. Gamma squared, plug them in, and calculate this number, okay? But to do the calculation, these are complex numbers. So I'm just going to put a couple identities that we need so we can integrate this very easily. So now integrate the gamma squared with respect to x. And del W will equal to pi h1 g double prime, and the integral will be from minus L over 2, and the minus will disappear now, and we'll have epsilon b star h1 squared shine squared x over b asterisk divided by cosine squared L over 2 b an asterisk and dx. Okay, we don't need this anymore.
The epsilon 0 d star should be squared.
Squared, yes sir. I'm gonna just put some identities. The first one, G asterisk. I'm gonna call this G cosine theta plus I sine theta. I'm going to call this G cosine theta plus I sine theta. So this is in effect saying that this is G cosine theta. If I factor out the cosine outside, so this would be 1 plus I tan theta, or I eta, and this eta will be the loss factor of the viscoelastic, for the viscoelastic material. This is cosine theta. This number is the G prime, and this is the storage modulus. Then accordingly, G double prime is equal to G sine theta. G sine theta. So that's the first one. Okay. Second one is the B. The B asterisk is here. This is the square root H1, H2 and E2 divided by G asterisk. This will equal to the square root H1, H2, E2 divided by G asterisk is from here. is G cosine theta, I sine theta. So now I'll multiply by the conjugate number, the numerator and the denominator. So the denominator will be cosine squared plus sine squared is 1. And this would be H1, H2, E2, and G. And then here we have cosine theta minus I sine theta, the whole thing, under the square root. This would be H1, H2. And then this number now, I'll put it in exponential form. So this would be E to the minus I theta. And then now we can clean this. And I'm going to call this alone. Exactly like we have here. This is a complex number, so we call this B complex. I'm going to call this just B 0. This is real number. This is real, and real. And it is the square root of this. Now the square root of what we have here is exponential e to the minus I theta over 2. So now I can expand this. Becomes B0 cosine theta over 2 minus I sine theta over 2. Now we have this, which we need here and we need here. Okay? So number 3, identity. I'm going to get the x over b asterisk. The x, we know it. The b asterisk is right here, is b0. And then I have cosine theta over 2, I sine theta over 2. So now we have this will equal to x over b0 cosine theta over 2 plus I sine theta over 2. And I'm going to call this u I v. And the u is x over b0 cosine theta over 2, and the v is x over b0 sine theta over 2. And I don't need all this. All these steps are missing in the paper, so when you try to drive it, you will spend an awful lot of time. It's very easy. L over 2, and this will equal to, I'll just plug in, and instead of the x, I'll put L over 2 here. So, so this will be x over beta 0 cosine theta over 2, I theta sine theta over 2. And at x is equal to L over 2. So this will equal to L over 2 B0 cosine theta over 2. And I'm going to call this U1 I V1. The U1 is directly L to B0 cosine theta over 2, and the V1 theta over 2. Now we can go directly now and calculate these two numbers. Calculate these two numbers. Then now number 5, the sine of x over b0 over B asterisk will equal to the sign of complex number of U plus IV. So this is very similar to sine or cosine of sum of two angles. Sum of two angles. So this will equal to sine U cosine V plus I cosine U sine V. And of course, we can get the sine squared x over b asterisk. So the complex number will disappear and will be cosine sine squared, cosine squared, cosine squared, sine squared. Okay, we have the V, and we have the U, so we can plug in here, and this will reduce to sine well, I'm not going to write it because it's very messy, huh? But you just take the U and the V and plug in from here, and then now we can integrate this. Integrate minus L over 2 dx, and the result will equal to B0 divided by sine theta, and then times sine L over B0 cosine theta over 2 sine theta over 2 minus sine L over beta B0 cosine theta over 2 cosine theta over 2. So this is one part of this integral. Okay. Now the denominator is independent of x, but again it is cosine squared. I have to expand it using the same relationships for the sine and cosine and the sum of complex numbers. Number 6, the cosine L over 2b asterisk. We have the L over 2b asterisk here, u1 and v1. So this will be cosine u1 plus I v1. So this will be cosine the u1 cosine v1 I sine u1 cosine sine v1, and then the cosine squared will be the square of these numbers. And this, if we plug in these, then this will come to be 1/2 cosine L over V0 cosine theta over 2 plus cosine L over B0 sine theta over 2. The values here, the U1 is L over 2B times the cosine. So the cosine squared, I'm going to convert it to twice the angle. So the 2 on the denominator disappears. And it becomes this equation. Now we can assemble all this, and we have the final result. Then now the energy dissipation per unit cycle per unit width, because the length I put it in the integration. So now this will equal to 2 pi epsilon squared H2 E2 L B0 over L and then this shine L over B0 cosine theta over 2 sine theta over 2 minus sine L over B0 cosine theta over 2 cosine theta over 2, and then the denominator is cosine L over B0 cosine theta over 2 plus cosine L over B0 sine theta over 2. And from here there's one very important parameter, is this parameter. And this parameter, and I will say here let L bar be the dimensionless length of the constraining layer. And why? Because this L over B0, this is length. B0 is right here. This is Young modulus of the top layer. Shear modulus real of the viscoelastic. So these two are the same units. This is meter squared or length squared under the square root, so it is meter. So this is dimensionless number. This also is length. But now it has everything built in it. It has the thickness of the viscoelastic, the thickness of a constraining layer, their relative stiffness, longitudinal and shear. Okay. Now, if we look at the front number that we have here, okay, before we look at this number, what is left inside the term between brackets is one parameter, which is this theta. Again, if you remember, we said tan theta is the loss factor of the viscoelastic material. So now for a given material, this theta is known. This theta is known. So everything is known inside the brackets in terms of the theta and the dimensionless number length of the viscoelastic constraining layer. Now if you look at the term here, this term here is, I can rewrite it like this. Okay? So now this is stress times strain. Stress times strain is energy times H2 and L, so it is energy per unit width. Energy per unit width. This is energy per unit width. Okay, so now I'm going to make this dimensionless number. I'm going to divide this by this. So it will be dimensionless energy dissipation over this. Okay, so now I'm going to make the final value. I'm going to make this del W divided by this, and then we have only a parameter, which is the 2 pi. I'm going to put them here. And this number will equal to this. And to make this energy, I'm going to multiply it by 1/2 here. And when we multiply by 1/2 here, I'll multiply here by 2. So this becomes 4. So now this number is how much energy we dissipate in the viscoelastic material. This is Young modulus of the constraining layer. H2, the thickness of the constraining layer. So this is, everything here is related to the stiffness of the constraining layer. Everything here is related to energy dissipation in the viscoelastic material. So this number is how much I dissipate for a given strain in the constraining layer. So I'm going to call this number another energy loss factor of the entire assembly. Now we can come here. And draw this. The beautiful thing is, for any viscoelastic loss factor, or for any theta, I can plot this parameter in terms of B0 and L, dimensionless length. So I'll put the material, so this will give me theta. I'll select any LB, so I can plot this characteristic. And now I vary the material, so we'll have something like this, All of them come here, and one universal number, which is 3.28. And this man, Blanket, is the National Academy of Engineering. He's has fantastic place in engineering, because this number is a magic number that you use for any constraining layer treatment. So now, if you want to design, as we have here, segmented constraining layer, you just come calculate this number. This number is H2, H1, E2, G, under the square root, you calculate this number. Thickness of the viscoelastic, thickness of the constraining layer, properties of the constraining layer, the viscoelastic material, you have this number. You multiply it by 3.28, that's the length of the constraining layer that you should have. This applies also, as you will see next time, to the transverse vibration. Have a fantastic evening. We'll see you on Thursday. Get the paper and see the derivation of the paper is 3 lines, and everything else is left to you. Okay? Fine, have a good evening. U at any position X. And we determine this for base structure that is oscillating at constant strain. We wrote down the equation of static equilibrium. And we found that this will equal to the and we said here where the V aspect squared is equal to H1, H2, E2 divided by G aspect. And this is the complex shear modulus. We said that this is equal to some G sine theta sine theta. And the solution was made of 2 components, U complementary function, U particular integral. And we found that this is equal to epsilon 0 over shine. Over shine, I'm sorry. And from here we determine the shear strain. Gamma, and this is equal to U minus U0 divided by the thickness of the viscoelastic material, H1. So this is U minus epsilon 0x over H1. And this was equal to then we took this expression, we said now we want to get the energy dissipated per cycle per unit length, per unit width, or we will do it like this. This was B H1 G double prime and gamma squared. And the total energy dissipated in the viscoelastic material will be the integral from minus L over 2, and this will equal to pi B H1 G double prime integral gamma squared and dx. I did not prove for this, but this is very easy from vibration class, first vibration class. This is dissipated per cycle. Okay. So now from here, we determine the energy dissipated, and this expression we call it del W, and if I take this del W and divide it by 1/2 epsilon squared B1 H1 and L and E2 then this will equal to 4 pi B0 over L. Then here I'll condense it in this form. Shine variable A sine theta over 2 minus sine variable B cosine theta over 2, and then divided by cosine A plus cosine B, and here is where the A and the B are L over B 0, cosine theta over 2, L over B 0, sine theta over 2. And we call this eta of the assembly, eta A. Then now we said eta A is function of two variables, function of L over B0 and theta. And tan theta is equal to loss factor of the viscoelastic material from here. So this will equal to G cosine theta, 1 plus tan theta I, 1 plus A tan I. So now from this equation, I can draw graphs like this. And each one of them for a different eta V. And eta is increasing in this direction. And people that developed this theory found out that there is a universal optimum, and this is at 3.28. Now, again, as B0 is equal to the square root of H1, H2, E2 divided by G. From this equation, this is complex, and this is complex, but B0 is the real part of all this. So, for example, if I take a constraining layer of aluminum and a viscoelastic material, the one that we've done an awful lot, the 606 diet 606, and I'm going to take these two layers, each one of them 10 thousandths of an inch. And this is typical. Aluminum as Young's modulus is equal to, and I'll just make it very simple, I'll just make this 10 to the 6. PSI. And the diad 606, for most of the range that we were working with for maximum loss factor, this as G. If you look back in the homework problems, you'll see that this is 10 cubed pound per square inch. Now let's plug these numbers here. Then B0 will equal to square root ten thousandths of an inch, 10 thousandths of an inch, 10 times 10 to the 6 divided by 10 to the cube. So this will equal to 10 to the 4 times 10 to the minus 4. So this is equal to 1. And the units of this is inch, this is inch, pound per square inch, pound per square inch. So we'll have inch squared under the square root, so this would be 1 inch. So now if I want to design a good constrained layer damping, then I have to select the length optimum such that L over B0 is equal to 3.28, and this means the length of the constraining layer should be 3 1/4 inch. Okay. Important thing is here, this number. Over this number. This ratio is almost 10 to the 4th. Okay? So now what I'm going to do is I'm going to remove this constraining layer. And then we'll do the energy dissipation when it is unconstrained. And then compare what will happen if we constrain the viscoelastic material. The analysis is very simple in this case. For unconstrained. So now this configuration will look like this. I'm going to stretch the base structure with the same strain, constant strain, and the viscoelastic layer will follow it. So now I can calculate D del W when I have unconstrained case. To look very similar to this. Here, I have the area of the cross-section of the viscoelastic material. Pi comes from, I'm averaging over one cycle. So I have the integration of the sine squared from 0 to t1 over t, so this comes to the pi. So this will stay as it is. Now, in the first case that we've done, because I'm putting the constraint layer, I am shearing the viscoelastic material. So I'm using the loss modulus in shear and the corresponding deflection in shear. Now here, we'll have very similar. We'll have pi, b, h1, and then instead of the shear modulus, I'm stretching everything in longitudinal motion. So this will be one double prime. The viscoelastic material, E double prime. And then, instead of gamma squared, I have epsilon squared. Now in this case, we're very fortunate because epsilon is constant. So when I want to get this and determine the total energy and integrate over the length, epsilon will go outside and the integral will be very easy. So now here, then the total energy dissipated will be del W unconstrained will equal to pi B H1 E1 double prime epsilon 0 squared and the length of the viscoelastic material. Or let's just do it like this. Now I'm going to get the expression that we have for this, and then get the ratio between them. Get the ratio between these two expressions. Now we'll call this equation 1. shear case where we have constraining layer. And del W constraint is equal to pi b h1 g double prime integral gamma squared dx del W constraint over del W unconstrained. This will equal to here pi BH1 E1 double prime L epsilon 0 squared, and this will equal to pi BH1 G double prime dx. Okay, so now I can drop a lot of terms, these with these, and then now these two. I'm going to assume the following. Again, G is equal to G prime I G double prime, and this will be equal to G prime 1 plus eta I, and will look very similar to this. Will look E prime 1 plus same eta I. This is legitimate for any isotropic material. The damping in any direction will be the same. If I shear the material or expand it, it will be the same. So these are exactly the same properties. So this says now, then G double prime is equal to G prime and eta. E double prime will equal to E prime, also eta. One more thing, we know that G prime is equal to E prime divided by 2 times 1 plus Poisson ratio. For viscoelastic material, the Poisson ratio is approximately 0.5. Then we have G prime is equal to E prime over 3, or G double prime now is equal to eta and G prime, and this will equal to eta and E prime over 3. Eta and A prime is equal to E double prime over 3. Then I can take this ratio, G double prime over E double prime, and replace it by 1/3. So, in spite, like we want to show that the numerator is higher than the denominator. The numerator is higher than the denominator. But if we use the material in tension, this number is 3 times higher. But this is all noise, because the big chunk of the improvement of the constraint relative to the unconstrained comes right here. So in spite I'm dividing here by 3, this number you will see will be 270, 300, will be much, much higher. Okay? So now we're done from this, then we'll look at the remaining part. And now I'll just call this the ratio, which is del W constraint, del W unconstrained, and this will equal to three L, and then epsilon 0 squared, and then the integral from minus L dx. Now we have the expression for gamma. We integrate this expression, and the result will be third H2 over H1 and E2 over G B0 L sine theta, and then this big expression sine H E sine theta over 2 minus sine B cosine theta over 2 cosine A cosine B. Again, the A and B are the same as we had before. L over B 0 and the B L over B 0 sine theta over 2. Now it comes in a very nice form. This is dimensionless number. This is dimensionless number. This is dimensionless number. Ratio between the constrained layer and the viscoelastic layer thickness. Young's modulus of the constraining layer and the shear modulus of the viscoelastic material. The characteristic length, which we found to be equal to H1, H2, E2 over G. But we will not use this number. I'm going to use the best constraining layer, which constraining layer that has this ratio, 1 over 3.28. So now the A depends on this ratio, and the viscoelastic material viscoelastic loss factor. Then now here, I'm going to use eta viscoelastic is equal to 1. This is very similar to the diad 606. So this will give us the angle theta is equal to 45 degree. I'm going to use L over B0, the best viscoelastic constrained layer, 3.28. And then I'm going to make the following case. I'm going to take H2 over H1 is equal to 1. The thickness of the constraining layer, the thickness of the viscoelastic is 2 to 1, okay? And then E2 over G. I'll leave it for a minute. You calculate this number. For this material, then you'll see that this number is 0.124. Then the ratio is equal to 2/3. I'm going to take this as 1, and then this last bracket is 0.124. Okay, and then now the ratio between E and G, if I use the case of aluminum and diode 604, this ratio is 10 to the 4. 10 to the 4, okay? So if I multiply this times this is almost 1,000. When I multiply by the 2/3, okay? 1,000 times. 1,000 times. Now if you make this very thin constraining layer 0.1 and I have 1,000, the benefit is 100 times. So very thin sheet of constraining layer makes big difference in how much energy you dissipate in shear as compared to in tension. So this ratio is approximately 1,000. Okay, and this is the main reason for using constraining layer. So the bottom line of all this, I'm penalizing myself because I'm using a soft modulus compared to a very rigid modulus, but I'm compensating for this by very large shear deformation as compared to the longitudinal deformation. This is one proof, and then we'll do one more, hopefully end of today or next lecture. So the summary of all this, constraining the viscoelastic material makes it deform in shear and results in significant or significantly high energy dissipation characteristic. I want to make a couple of notes first. The blanket and the analysis. Assumes two things. Number A, quasi-static analysis. And this is justified by saying the constraining layer is very thin, that the inertia I can neglect. Is thin, then its inertia is negligible. Second thing is which is very important. We looked at viscoelastic material property. We looked at constraining layer material property. These two things, I am using them to dampen this structure. We did not mention anything on this structure. Nothing. Steel, aluminum, we did not mention anything on this structure. Okay? So the assumes a general base structure. So these guys had fantastic vision, you know, like almost like looking in a crystal ball. If you make this analysis for a plate, you'll come with exactly the same number, 3.28. If you use a plate, you will come exactly with the same number. And you could see this very easily, that we also did all this analysis looking at longitudinal vibration. But this can equally be used or applied to transverse vibration. General base structure. Number 3, longitudinal vibration. Now let's take here why this is very nice. Let's take a beam and I'm applying moment on this beam, for example. And I put here my viscoelastic material and my constraining layer. Let's say that this distance is little d. And the strain at the base of the viscoelastic material this strain I can write it down as the distance d times the curvature, which is partial w partial x square and square. The bending moment I know it is equal to EI. So if I give a constant bending moment, the curvature is constant, the strain at the base of the viscoelastic material is constant, and I can call this epsilon 0. Okay? So now I can analyze bending using the same formulas that we have. Exactly the same. Now, I want to get here energy dissipated for this example, for example. We just say that this is a small l, and this is still my capital L. The energy dissipated in the constrained layer is still the same. I can calculate it exactly as we've done before. D del W, constrain the layer. The same story as we have. Pi B H, G double prime, integral, dx. And this will be the total. Okay? Now I want to get an estimate of the loss factor. Try this, have room. And if you remember, gamma was equal to minus epsilon 0 shine x over b star, and then here cosine L over b star. So now gamma is not only function of x, but it is function of epsilon 0. Epsilon 0 is function of the curvature of the beam. So now I have to take this and put it inside the integral now. So now then del W will equal to G double prime star squared, and then we have shine and then I'll replace this from here. Now for example, if I want to calculate the loss factor,
I think that should be hyperbolic cosine
Squared.
L over 2b. So,
2b.
yeah.
Okay, now, for example, if I want to get the energy loss at the first mode of vibration of this beam, then I take the curvature corresponding to the first mode of the curvature. Function of x, integrate, get the energy loss, and then we can put it in the normal dimensionless form as we've done before. Divide this by the number that we get, very similar to what we had here, which if you remember, this was the number that we normalized over the last time. So we can calculate from here the loss factor. Second mode of vibration, the same story. Then now the loss factor of the assembly will equal to del W constraint divided by some del W nominal. So the same analysis that we did for longitudinal vibration, I can extend it for transverse vibration. And this is super important thing to keep in mind. This was done for any general structure. And there are people that did the same for plate, the same result. And this assumption, in spite of the fact that we're looking at static case, the results are very close to the optimum if we have the dynamic case. Okay, any questions? I want to just give you a little exercise. You can do it by home tonight. It's very simple. I have a base structure, 1, and then viscoelastic, 2. H1, H2. And the first class of strengths of material show that the above composite has total inertia, flexural rigidity, which is this plus this, around the neutral axis, is equal to 1 plus R where RE is equal to E2 over E1, and this is asterisk, and this is asterisk, equal to E2 over E1, and this is equal to RE1 plus eta I. Show that as number A, yes. So for example, if I don't worry about the neutral axis, I have here Young's modulus times thickness cubed over 1 over 12. 1 over 12 Young modulus, thickness cubed, and then divide by 1 over 12 Young modulus 1 over thickness cubed. So when you do the reduction, one of them will be G over V1, and the second will be the ratio of Young modulus, and and the ratio of thickness cubed. This comes because the neutral axis is not any place. It has some specific location. Okay? Now, this R is given by this. I want to calculate this eta. So now I'm going to come here, replace each one of these by this, and substitute it here. And when you do, the number B, show that this eta will equal to RE, RH eta viscoelastic, which is eta 2. Then the denominator will be 1. The last thing that we want you to show, number C, eta, instead of this miserable expression, we can approximate it by Tuesday, next Tuesday. This is very nice expression, and we have very similar expression to this case. A 3, instead of 2 layer, we have 3 layer. And if you have the general case, the 3 layer, and put the thickness of the top layer is equal to 0, you reduce to this case. And this will show you another proof. The loss factor for the constraining layer will be much, much higher than the loss factor if you remove the constraining layer. Okay? All this was done by Unger and Kerwin, 1959. That's the original paper that they did on this idea. This is in Journal of Society of America. Just a little example here, if you. Yes, sir.
The RH.
Oh, I'm sorry, I did not say this. Where RH is equal to H2 over H1, the thickness ratio. And the RE is the Young's, the storage modulus ratio. Example here. going to take again RH, which is H2 over H1. I'm going to take it as 1. And then RE, we'll take it 10 to the 4 as, no, take it different than 10 to the 4. This is 3.585, that's from their work, minus 4. So the viscoelastic material here is diet, and then this is aluminum base structure. So E2 over E1 is this number, which if you remember from the E and the G was almost 10 to the minus 4, because the ratio was of the E to the G was 3. So this is approximately this case. And if we take this and plug it in, B, then eta will come to be 502, 005, I'm sorry, times eta 2. If you use formula C, then eta will be 0.00519 eta 2. So this formula is very powerful, exactly like the magic number 3.28. If you want to design viscoelastic material with back of the envelope type calculation, these are the two numbers that you need. The 3.28, and then you take this, you can calculate immediately the loss factor of the material. Now loss factor of the viscoelastic material depend on the frequency. So at any resonant frequency, you determine from the table of the material E2 for the viscoelastic. Multiplied times this, you determine the corresponding value of the assembly of the structure and this. This is also relates very nicely to some work that is done how to calculate the loss factor of material using finite element. Finite element codes don't have viscoelastic material elements. They require to give them this number. What they do, they use modal strain energy. So you can look at how much energy you use to strain the viscoelastic material compared to the total strain energy of the structure. And then you take this ratio, multiply it by this number, and the program will give you this number. It does not have GHM, it does not have ATF, it does not have any of these things. It gives you a ballpark estimate using very similar analysis like what I did here. So if you look at this, this is the total energy, strain energy of the assembly. This is the strain energy of the structure. From these two, I get this ratio. That's what finite element packages do. They look at the total energy, the number that you give them to designate the viscoelastic material, they take this number, multiply times this ratio, and then give you the modal damping ratio for your case. No commercial finite element package has any of the GHM, ATF, or any one of these models. And the only method that they do it is very similar to this very simple case. Okay. Now in the remaining few minutes, so let me go now, and we want to generalize this to 3 layer assembly. we look here at kinematics. Of constrained layer depth. I have here 3 layers. And then I'll deflect them, they will look like this. So, for example, the top layer will move from some data. Some distance U1. The bottom layer will move from the same datum another distance U3. The viscoelastic material will look like this. For example, I'm taking some place here. This is H1, H2, and H3. I'm going to call this point A and B. This distance is the slope of the deflection line, which is partial W by partial X. This is the same. And this is the shear angle of the viscoelastic material. Now I can calculate U A is equal to U1 plus the slope times H1 over 2 Wx. And I can calculate UB is equal to U3, and then I'm going back minus H3 over 2 Wx. The difference between them will be this little distance. UB minus UA will equal to U3 minus U1 and plus UB minus, so this is minus H1 H3 over 2 Wx. Okay, did I make a mistake? Okay, so now this little distance is UB minus UA. Now I'm going to make a little triangle like this. From here, I'm going to drop this vertical line to here. The blue line has distance is equal to H2. Okay? These two triangles are similar. Okay? Why? Because this angle is equal to this angle. This angle is 90, this angle is 90, so this little angle is the same like this little angle. Okay? Now, this is 90. Okay? Now, this is 90 and 90. And this angle and this angle have these two equal, so the little ones should also be equal. So the two triangles are exactly similar. So if this distance is H2, then this white distance is also H2. Then now, the little angle here is the difference between Wx and gamma. This little angle, I can write it down in terms of the tangent, UB minus UA over H2. So now from here I can write down the shear angle. I'll bring this here and bring everything else on the other side. So this will be Wx H2. Let's take this for a minute, so we don't make mistake. Gamma, I'll bring it here. So this will be Wx minus this. So this would be UA minus UB over H2, and then it is plus. Okay? So now we can clean it. I'll have everything over H2. This would be H2 Wx, then UA and UB are right here. I'll take the difference, so this would be U1 minus U3. The minus becomes a plus. And then we'll have here H1, H3, and the final result will give us the very famous equation for constraining layer damping, and here where the H is equal to H1 over 2, H3 over 2 plus H, which is this distance. H1, H3, H2. So now next time, we'll say, I want to now write down energy of this system. I want to write down the equation of motion of this system. Okay? If we write down by partial differential equation, we can spend the whole semester. Write down by finite element, very fast. Write down the finite element for this, finite element for this, finite element for this. So I have U1, U3, and then the deflection, W. I have the shape function for this, the shape function for this, the shape function for this. I can write down everything in the strain shear deformation, get how much energy I put in the viscoelastic material, we get the stiffness matrix and the mass matrix for the entire assembly. We'll do this next week. Have a good weekend. We'll see you. This work is done. The original work was done by Unger and Kerwin. These were closed form mathematics. But then all the work in this area was done by one man in University of Southampton, the Institute of Science of the Vibration and Sound. And his name is Dennis Mead. He's done all the work in this area. And he has a very nice book on passive damping. If you have money, you can buy it. $150 some dollars. So, but it's a very nice book. Fine, have a good evening and we'll see you next week.
Dr. Bowles,
Yes, sir.
we still having an exam on Tuesday?
No, we're not going to have an exam. Will be on May 4 is Friday. 5, 6, 7, 8. Will be May 8.
It's the final exam.
Final exam. I missed the 2 lectures, and then I will miss 1 more lecture on May 10. So we'll have 3 more lectures after May 15, and then we'll decide on the final exam after this.
Exams May 8.
Okay, have a good evening, and we'll see you next week.